The next paper that we are going to have on this live stream is from Germany, from the colleagues from Aachen. It is led by the principal investigator Günther Schuh and his colleagues Rebentisch, Michael Riesener, Thorben, Ipers, Tönnes, Merle-Hendrikje, Jank. And it is entitled Data Quality Program Management for Digital Shadows of Products. We are interested to see the presentation.
Thanks for joining the presentation on our research on data quality program management for digital shadows of products. My name is Thorben Ipers. I'm from the Laboratory for Machine Tools and Production Engineering of the RWTH Aachen University, and this paper was a collaboration together with the Massachusetts Institute of Technology, MIT. Our research is motivated by two trends. On the one hand, we have an increasing data volume that companies have to deal with every day. There is, however, a novel information system concept called the digital shadow, which promises to be capable of dealing with these growing data volumes. On the other hand, we have the data at the foundation of the digital shadow, but this data is only useful when it is available in a certain quality. And we take these two trends, the growing data volume and the digital shadow on the one hand, and the data quality on the other hand, together, and from these two trends emerges our research question. How can the quality of the databases of the digital shadow of products be optimized? To answer this question, we use design science research methods to develop a methodology for the data quality program management. Before I begin, there's in particular one term here that needs to be defined precisely, which is, of course, the digital shadow of products. The best way to define it is to contrast it with another term in this area, the digital twin, which is presumably even the more common term used throughout literature. But there's an important difference between the two. The digital twin is often described as the comprehensive representation of physical objects. That means, as you can see in the quote on the slide, it describes objects from the microatomic level to the macrogeometrical level. And in contrast to that, the digital shadow of products is only the sufficiently precise representation of real-world objects. I would even go as far as saying that the digital twin is utopian, whereas the digital shadow is what can actually be achieved in reality. And then we say digital shadow of products because we refer here particularly to a virtual representation of physical products. The methodology for data quality program management, which we have developed, is divided first into two phases: the assessment phase on the left side and the improvement phase on the right side of the slide. The assessment phase means that we want to evaluate the available data quality and derive potential needs for action. The second phase, the improvement phase, aims to set up projects for data quality improvement that are then bundled in a project program. If you look at the assessment phase, you can see that it consists of 3 steps corresponding to 3 submodels that we have developed in the paper. In the first submodel, we look at the different applications of the digital shadow in the company. In the second submodel, we consider the evaluation of the importance of these use cases with regard to overall company goals, because our goal is to prioritize the use cases and hence the data that underlies these use cases. In other words, the first 2 submodels give us a first factor to prioritize the data by use case importance. But we have a second factor which comes in the third submodel. In this submodel, we look at the actual data quality deficiencies and we want to evaluate in which databases these deficiencies are particularly severe, giving us the second factor, the data quality gaps. The 2 factors combined allow us to evaluate whether we have need for action, namely in databases with highly relevant and relatively deficient data. Needs for action are then targeted by data quality improvement projects. To this end, now in the improvement phase, we have one submodel which considers the configuration of data quality improvement projects. And I will now explain the 4 submodels in detail. If we want to evaluate which data has particular importance to a company, we have to look at the way the data is used within the digital shadow. We do this by looking at the different use cases of the digital shadow. What you can see on the slide are some prototypical use cases of the digital shadow throughout the product lifecycle, which is here structured into the 4 phases: define, realize, use, and retire. It needs to be said that our paper focuses on common expectable use cases, particularly for companies that produce physical products. So for other companies, slight adaptations need to be made, but also for companies with physical products, our descriptions are only of prototypical natures and adaptations need to be made or additions need to be made. But what is even more important here than the use cases themselves is the infrastructure of the digital shadow. What you can see is that we have different data sources which are integrated by the digital shadow to deliver information to the different use cases, where each use case has its own unique information requirements and also information quality requirements. Now that we have described the use cases, we want to evaluate the importance of these use cases in an organizational context. To do this, in the paper we have developed the digital shadow benefit impact model, which you can see on this slide. The benefit impact model consists of 3 dimensions: the strategic dimension, the managerial dimension, and the transactional dimension. And the model allows to rate the beneficial impact of the digital shadow with regard to overall company goals. As you can see, each dimension is further broken down. For example, the strategic dimension consists of customer alignment and competitiveness, architectural efficiency enhancement, and business innovation. Although we have so many factors, what we need in the end is just a single weighting factor for each use case. To achieve this, we are using the analytical hierarchy process. Maybe you already know the analytical hierarchy process. It consists of a number of pairwise comparisons. And in our case, it's first a number of pairwise comparisons of the use cases with regard to the factors of the benefit model, and then a pairwise comparison of these factors with regard to defined company goals. Like this, the single factors can be aggregated to importance weightings of each use case. As you can see in the example on the lower right corner in red, we have here 3 exemplary use cases, and each of these use cases gets 1 importance rating, 1 weighting factor to determine its importance. With the use case importance rating, we have a first factor determine our needs for action. But as I've said, in our methodology, we use a second factor, which depends on the severity of the data quality deficiencies. In order to evaluate the severity, we have developed a data quality model in submodel 3. Our data quality model has been derived from the plethora of existing data quality models in literature, but it makes a precise differentiation between information quality and data quality. As you can see, we have 6 information quality dimensions which structure the model, and then we have a number of data quality features which are assigned to the information quality dimensions and which are measurable attributes of the data. For example, we have the information quality dimension reliability, and reliability is expressed by the data quality features correctness, preciseness, and level of detail. One very important aspect in the context of data quality is the fitness for use principle. The fitness for use principle states that data quality is only meaningful with regard to the required data quality of certain application cases. So we cannot just measure the data quality features themselves, but we have to relate these measurements to defined quality targets, to a required data quality. We do this in our methodology by defining not only one singular requirements, saying that, for example, 80% correctness is what we want to achieve, but we define an interval of acceptable data quality with a lower bound and an upper bound. When we have this interval, we can now measure the data quality features and locate it somewhere in the interval, and then translate this location into a 0 to 100% relative data quality gap. The benefit of this method is that regardless of the unit in which the data quality features are measured, for example, processing speed, which is measured in a time unit, whereas preciseness is measured in a percentile unit, but regardless of the unit, we always have a relative data quality gap between 0 and 100%, and this makes the data quality features comparable. So we now have our 2 factors. First, the factor for the data quality deficiency, and second, the factor for the use case importance and hence the importance of the underlying data. And we can use these 2 factors to prioritize our needs for action. what we get is then a matrix of the weighted needs for action. The matrix has two axes. On the one axis are the databases, and on the other axis are the data quality dimensions. And from the matrix, the databases and information quality dimensions with the most severe need for action are selected and targeted with specific data quality improvement projects. The selection of needs for action can follow, for example, the Pareto principle. To support the configuration of a single data quality project, we provide in our paper a morphological box, which provides design variables in the design fields project type, responsibilities, and project extent. With regard to the information system, the application context of the database, and organizational characteristics, the project can be configured by selecting suitable variable values from the morphological box. An example can be the first variable, which is the orientation, and which can be corrective or preventive. The choice of this variable highly depends on the type of data that we are looking at, where frequently changing data is potentially better addressed by preventive measures than corrective measures. The final step is then the implementation and execution of the data quality project, which is, however, beyond the scope of our research. In design science research, it is vital to evaluate the practical applicability of the developed methodology. This evaluation usually aims to ponder the so-called, it's a common term, pragmatic success, which comprises both the efficiency and the effectivity of the artifact application in praxis. To do this, we applied our methodology in an industry use case at a German wind turbine manufacturer. As a result of this, 4 use cases were defined that sourced their information through the digital shadow from 9 data sources. As a result of the analysis, we defined, with the help of our morphological box, 6 specific data quality projects. Some of them have already been implemented by now by the wind turbine company. Now, if we look at the efficiency and the effectivity of our methodology, we see first on the side of the efficiency that we have one downside regarding the problem dimensionality. As you can imagine, already this matrix of databases and information quality requirements grows quickly in its dimensionality, so many inputs are required for our methodology. Nonetheless, we received the feedback from the data quality experts of the company that our methodology is a comprehensible and structured approach to the problem. Now let's look at the effectivity. Regarding the effectivity, there was one really interesting insight, because the result from applying our methodology was pretty much congruent with the intuitive a priori data quality expert estimates. And this tells us that our methodology is able to produce quite reliable outcomes. Furthermore, the data quality experts confirmed the suitability of our methodology for assessing data quality on the one hand and then deriving a suitable data quality improvement program. Okay, with this, I've reached the end of my talk. Thank you so much for your kind attention. I'm looking forward to answer any of your questions in the Q&A session.
Thank you very much, Thorsten Ipers, for doing the presentation and sending the paper in here. Data Quality Program Management for Digital Shadows of Products. We're now connecting to Thorsten Ipers from Aachen. Hello, this is Franz Dietrich from Berlin, 7th CIRPe Global Web Conference. Can you hear us?
Yes, I can hear you.
Thanks for joining us and putting the effort in the paper and the presentation. While watching the presentation, the question arose about can you clarify a bit more your understanding of digital shadows and digital twins?
Sure. So I think the term digital shadow is quite a new term, and it's not so widespread throughout the literature compared to the digital twin. The digital shadow is also a term that is more common in the German literature at the moment, I would say. But as we've said in the presentation, we see an important difference there. If you look at many of the definitions of the digital twin, you can see that one important point many authors make is that it is a pretty comprehensive representation of a real object, a comprehensive virtual representation. There's, for example, this quote of the microatomic to the macrogeometric level, which really well describes this comprehensiveness. And compared to that, the digital shadow is, as I've said, mostly in the German literature, often defined as the sufficiently precise representation of a real object. So there is already a selection of only the data and information that is important for certain use cases. So if you have a number of use cases where you want to use this digital infrastructure, then you have a selection of data and information that are provided to these use cases.
Okay. Yeah. Thank you very much. That brings me to the second question. We have 3 more minutes to discuss. How does that very conceptual work that we have seen right now, how does that get to use in real life application? What are the steps to be taken for that to be applied in practice, and how does it do you see very beneficial cases for that, or what is the application like that is very successful at that?
Yeah, the practical application was really important to us while developing the methodology. We used design science research, which has the goal to develop applicable design artifacts. And therefore, this applicability was paid a lot of attention to in all of our submodels. That basically means that most of these submodels really have factors that can be measured or can be determined. And if you determine all these factors, you can go through the submodels from the beginning to the end and then derive actionable data quality improvement projects. And we've also applied our methodology in an industry use case that was at a German company, a manufacturer of wind turbines. And we saw there that using our methodology, we could indeed derive a number of data quality projects. And some of these projects have also been implemented by now by this company and already show first successes in improving data quality and making the digital shadow more usable.
Yeah, I reckon that to handle the complexity of all the data and all the interconnection is quite a challenge in such kind of applications. Is there any particular comment that you can make on that?
Yes, that is true. It's indeed quite a lot of input factors that are required. The way we implemented it at this company was using an Excel-based model. So all the inputs were made in Excel, but still it was a lot of effort to do it. But I think it's still a good support method for improving data quality efforts in a company, using these factors and making the efforts to get the results.
Okay. Thank you very much for being with us in this question and answer session for your paper. So all the best to the colleagues in Icon, and see you soon, or comment on the next papers. Thank you very much, and goodbye.
Thank you so much. Bye-bye.
Bye. So this was the presentation and question and answer session for the paper Data Quality Program Management for Digital Shadows of Products, prepared by the colleagues from Aachen and Thorsten Ipers, live in this question and answer session.